In this video, I'm gonna solve the puzzle The Balancing Act 2, which was published on February 29th of 2024, an intermediate puzzle. And I'm gonna solve it using vectors. And vectors, I'm a big fan of them because they can really be nice when there's a lot of symmetry involved. And few people actually use them, but I'm a big fan of them. So I will use it here to solve this puzzle. What is the puzzle about? It shows two squares sharing one vertex. The squares need not be the same size, but what also is shown is a line segment from these two vertices, connecting these two vertices, and exactly halfway there is drawn a line to this vertex, and the question is what is this angle? Alpha. And what I'm going to do, as I said, is use vectors. Let's first make visible the vertices like this. And the first thing to do is to choose the origin of the vectors, and it is quite logical to use the point A for that. Because a lot of vectors are coming from that point A. So let's take this as the origin. Then we call this the endpoint of the vector B. So the vector B is from O to there. And we call this the vector A. So the vector A goes from there to there. And because this is a square, we call this RB. And what is R? R basically is a rotation over 90 degrees anti-clockwise. So if I rotate this vector to 90 degrees anti-clockwise, I get over here. So this is the rotation of B. And similarly, this is the rotation of the vector A, also anti-clockwise 90 degrees. Now, these points are the sum of those two vectors. You can apply the parallelogram rule, but of course it's a square, so it's even simpler. But this is the sum of B plus RB. That's basic vector algebra. And similarly, the point F is the endpoint of the vector A plus RA. Now, this leaves us one vertex to show, and that is the point H, which is the midpoint between these 2 points. And because it is the midpoint, it is half the sum of those vectors, so the vector B plus RB and the vector A plus RA, and half the sum of it, and that's also quite basic algebra, ends up at the midpoint. So we have that H is A plus, half, so half A plus RA plus B plus RB divided by 2. So that's that vector. Now, next thing to do is to draw the vector which connects these 2 points. So basically, this is the begin point and this is the end point. And what you know from vector, you subtract this from that. So this vector, which starts there and ends there, it is this minus that, so we have a half there, so we have A plus RA, and we have half B minus B, so the B gets a minus, plus RB divided by 2. You can work that out for yourself, but that's that vector. Also, this one can also be shown as a vector starting over there, ending over there, and it is of course that subtracted by that. So the same trick, we have A, and the RA switches sign, half RA minus RA, so it's minus a half RA plus B plus RB divided by 2. That's that vector. And now I'm gonna apply the anti-clockwise rotation on this vector. So if I take this vector and let's put it over here. So here we have. Sorry, I will. There. I'm gonna apply that anti-clockwise rotation over 90 degrees to A minus RA plus B plus RB divided by 2. So note that this vector, I apply the rotation on that. And what comes out, well, I can factor out the angle, so we have that it is R, okay, the half comes out, but it is RA minus R squared, so basically a rotation anti-clockwise over 180 degrees, but let's for the time being call it this, plus RB plus R squared again of B, and then divided by 2. So that's over here. But what do we know is that R squared is 2 rotations over 90 degrees, so it's a rotation over 180 degrees, and that basically is a multiplication by minus 1. It mirrors it in the origin. So R squared basically is minus 1, the operation. So if I apply that, so let's say is equals, and again the Ri, and then we have minus minus plus, so we have plus A plus RB, and again the minus minus B divided by 2. So we have used the fact that 2 rotations over 90 degrees add up to minus the identity. But now compare that to this vector, and what you see, it is exactly the same. So we have basically what we have shown is that if I rotate this vector 90 degrees, I exactly get this vector. And what does that mean? Well, a rotation over 90 degrees, that means that this is a 90 degree angle over here. And what's more, because a rotation keeps the length of the vector invariant, they both have the same lengths. So what have we established now? That this triangle is a isoscalous and also a right isoscalous triangle. And these are the same. The angle here is 90 degrees. It is a right isoscalous triangle. And what does that mean? That those two angles are 45 degrees. So we have established using vector algebra that alpha is 45 degrees.